Hello everyone, my name is Abulfaz Mahmoudpour, and in this video we are going to have some practice on applying of an internal boundary condition in solving of a partial differential equations using numerical methods. Our numerical method is based on finite difference, and I have chosen one-dimensional nonlinear Poisson equation that we have solved in the previous video. You can find the link for the previous video here. Therefore, you must first watch that video to be able to completely understand this one. This time we will solve the same problem in a double layer medium. Therefore, there is some internal boundary condition, and we will see how can we apply this internal boundary condition in matrix method calculation. So if you are interested, stay with me. Okay, this is the general form of one-dimensional nonlinear Poisson equation, and nonlinearity is due to the presence of this exponential term at the right-hand side of the equation. We know the boundary condition. Potential at the left boundary is some V left, and the potential at the right boundary is some V right. And because now we are in double layer, it means that the epsilon of the first layer is different than the epsilon of the second layer, and these epsilons are the relative permittivity. Thickness of the first layer is d1, thickness of the second layer is d2, and we know that at the absence of any surface charge density, the displacement vector at this point for the left medium and the right medium should be equal, and that is nothing but epsilon naught epsilon 1 e1 for the left layer and epsilon 2 e2 epsilon naught epsilon 2 e2 for the second layer. We know that this electric field is nothing but the minus derivative of potential with respect to the position. Therefore, E1 will be dV1 over dx, and E2 will be dV2 over dx. And we saw that we can decompose this equation into two equations. First one is nx, is this term, and the second one is term, but this is the linear form of this Poisson equation, and we saw how we can linearize this equation just by expansion of the by Taylor expansion of the exponential term. After such an expansion, we got such an equation. And what is next? Next is just if I multiply both ends of this equation with epsilon, I will get this equation, and now we know how to derive the discrete form of this equation. Discrete form will be like this, and you learned how to do this in the previous video, but this time we should keep in mind that hi here, indeed h is delta x, but because we may have different delta x for the first layer and the second layer, therefore instead of using some scalar, we use some array for the h, and because epsilon is different for the first layer and the second layer, therefore epsilon also should be some array instead of being some scalar. And after multiplying of the both ends of this equation with hi squared, we will get this equation. What is the next? And the next is discretization of the medium. We have the first medium, second medium. First medium have some grid, second medium have some other grid. We know the value of the potential here and here. That's why I have marked this grid and this grid with green color. And the grids for the left layer is with blue color, and the grid for grids for the second layer is with red color. But if you notice, there are some small circle here. Let's call this small circle with non-integer grid. If you notice to this big circle, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 for these big grids, right? And we call it with integer grid. These grids that are at the center of this cell, let's call this grid with non-integer grid. In a finite difference method, if we want to calculate the derivative of the unknown variable, first derivative, third derivative, fifth derivative, so on and so forth. If we want to have the odd derivative of the unknown variable, that here is vi, we will save this derivative of the odd derivative of unknown variable at the non-integer grid. And we will save the value of the function and the even derivative of the unknown variable at the integer grid. You should remember this one. And I have marked this grid number 5 with N1 because here, let's call it interfacial grid, right? We have some grid at the interface of layer 1 and layer 2, and we call it with some interfacial grid, and N1 here is 5 and the number of grid is 9. What is the next? So we have the discrete form of PDE, and by sweeping of I from 2 until 8, we will get this system of equation. And I have marked the fifth equation, 1, 2, 3, fourth equation. Fourth equation with a red color. Why? Because we do not use this equation to find the potential at the grid number 5, that is interfacial grid. What we use to find the potential is indeed the internal boundary condition that we discussed in the first slide. Calculation of that condition will give us this equation. Means that electric field here multiple to the epsilon 1 should be electric field here multiple to the epsilon 2. What is electric field here? V5 minus V4 divided by this interval, that is H4. And electric field here will be epsilon 2 multiple to the V6 minus V5 divided by H5. And after simplification of this equation and keeping V5 at one hand side of equation and the rest term at the other side, we will get such a equation that FR2, that stands for some fraction, is epsilon 2 H4 divided by epsilon 1 H5 plus epsilon 2 H4. And FR1 is epsilon 1 H5 over epsilon 1 times H5 plus epsilon 2 times H4. And now that we have derived this V5, we need to substitute this V5 at the neighboring point to the interfacial grid. At the equation corresponds to the neighboring point to the interfacial grid. And what is the neighboring point to the point 5 is 4 and 6. This equation shows the value of the PDE at the grid number 4. Therefore, we will put V5 from this equation once here, another time here. And this equation corresponds to the value of the PDE to the close to the this grid number 5, that's interfacial grid. What else? We know the value of V1 and V9 in external boundary condition. After sending out these two terms to the right hand side of the system of equation and after substituting out this V5 here and here, we will get such a system of equation, and I just substitute 0 to the coefficient of V at the left hand side and just substitute 0 to the right hand side because we do not use this equation. We will use what? We will use this equation for calculation of the potential at the interfacial grid, and we will use this equation and this equation for calculation of the potential at the neighboring grid to the grid number 5, interfacial grid. What else? After having our system of equation, we know how to derive the matrix form of the system of equation, and the matrix form is following. You can easily check if you multiply this matrix to this matrix, and for example, this row should multiple to the this column, and the right hand side will be this term and this term. It will give us the first equation, this to this and this second equation, so on and so forth. And if we have a look to this matrix, we have learned that we can generate such a matrix if we do not have any internal boundary condition. We saw that we can generate this matrix by this commands, or let's say by this equation. And you can easily check, for example, when I is 2, M22 will be this term, and that is nothing by AH3 squared times N3 over V thermal minus 2 epsilon 3. I is 2, therefore epsilon 2 plus 1 will be epsilon 3. Again, when I is 2, it will give us 1, 2. 1, 2 is this term, and 1, 2 is what? It is epsilon 2. Okay, therefore this one should be epsilon I. Again 1, then I is 2, will be 2, 1. Where is 2, 1 element? 2, 1 element is this one, and what is that element? That element is epsilon I plus 1. Therefore, if we do not have any internal boundary condition, we saw that by having of these commands, we can generate such a matrix inside a loop. But this time, because we have some other terms corresponds to the neighboring grid, to the interfacial grid that I marked with blue color here, we can see that 1, 2, 3, 4, 1, 2, 3, 4. Let's say when I is n1 minus 1, because n1 is 5, right? Therefore, n1 minus 1 will be 4. When I is 4, we should have a special term for this neighboring point. For example, we say that, okay, I is 4, therefore m33 should be like this, and it generates this term. If you substitute 4 instead of I, you will get this term. Again, if you substitute 4 instead of I, this term will be this one, and that is fraction 2 times epsilon 4. This term will generate this term, and this term will generate this term. Just we will see how can we generate such a matrix in the MATLAB. Just we will write this commands that you see here. What is the next? Okay, the next is we know that once we generate this matrix is unknown, and by calculating of the inverse of this matrix and multiplying to the right hand side, we can find the value of the unknown variable that here is potential. But we know that in calculation of the inverse of any matrix, when any row or any column contain 0, all element if are 0 for any row or any column, therefore the inverse of the matrix will be infinite. Why? Because we know that we should calculate the determinant of the matrix, and when we calculate the determinant of a matrix that contains all 0 row or all 0 column, it will be infinity. Therefore, the next step is to remove this column and this row. This column from this matrix, this column from this matrix, this from this, and this from this matrix. And this row, and this column, right? After removing of this row and this column, we will have such a matrix equation. Now we can easily calculate the inverse of the matrix M, and it will be M in power of -1, and by multiplying of inverse of this matrix to the right hand side equation, we can calculate this matrix. And here I call it with V underline CWI. This CWI stands for the potential at the central grid, because we do not have V1 and V9, but without internal boundary condition, because also we do not have V5. Therefore, we can calculate the VCWI. Yeah, that's it. And we found the value of the potential at the all unknown grid, and we know the value of the potential from the external boundary condition, and we know that value of the potential should comes from some internal boundary condition that we calculated in some slide here, and we found all the other unknown grid. So I think that's it for theory, and let's go to the MATLAB and see how can we implement this internal boundary condition in the code that we have developed previous time. Okay, this is the same code that we have derived previous time for one-dimensional nonlinear Poisson equation. I just want to modify this code and apply this time the problem to the double layer structure. Let me copy it, Control A, Control C, and create new file, Control V. Okay, and let me save it somewhere. Save as Okay, here. Okay, Poisson 1D, let's call it Poisson 1D double layer. Okay. Let's first have a look what we have here by pressing F5 and folder. Okay, this is indeed the convergence graph and shows the error. And this one is the potential, and the blue one is potential, and this dashed red line is indeed our initial guess. This time, because we are also interested to see the electric field, let's modify this code and try to have also the graph for the electric field. Therefore, let me define, if you remember, I mentioned that for the electric field, we need to have some, because electric field is the first derivative of potential, right? And we need to save the electric field at the non-integer grid, right? Okay. So let's write it here, and I want to define the non-integer grid with some x edge that stands for x half, and this is nothing but half x from 2 until n. I just want to add the two neighbor grids to each other and divide it by 2. Therefore, it will give me the center point of the cell. Again, half multiple to the x 1 and minus 1. Yeah, okay. And we know that the electric field should be, the dimension of electric field should be n minus 1. Zeros, n minus 1 and 1, because n is the number of grid, and when the n number is the number of integer grid, n minus 1 will be the number of non-integer grid, right? And let me define some e total, and the dimension for this zeros, n plus 1 and 1. I will explain what is this e total, and therefore let's sweep I from 2 from 1 until n minus 1 and okay, electric field at each grid should be minus the value of potential I plus 1 at the next grid minus value of potential at the current grid divided by h, right? Okay, and let plot electric field, and I just copy this commands from here and paste it here, and we want to plot electric field E versus x h that indeed shows the position at the non-integer grid, and let it be with some red color, and therefore this is x micrometer and this one is E electric field, and that's the unit is volt per centimeter. Press F5, and you see this is the form of the electric field at non-integer grid. And if you notice, we do not have electric field at the boundaries, at the left boundary and at the right boundary. Why? Because we have saved the electric field at this non-integer grid. And if we want to find the value of the electric field exactly on the boundary, we can have this just by linear interpolation of the electric field at this point and this point for left boundary. And for finding out the electric field here, we can easily find it by linear extrapolation of this grid and this grid. How? Okay, let's see. This E total indeed is what I defined for having the electric field everywhere, either in the non-integer grid also or in the boundaries. Therefore, let me define E left. We know that for a linear extrapolation, imagine that we have a line and the equation for a line is y equal to m multiple to the x minus x naught plus y naught. If we have some point x naught and y naught, and if we have m, that is a slope of this line, and this is nothing but delta y divided by delta x, right? By having of the slope of the line and having some source, let's say source point of x naught and y naught, we can calculate the value of this this line at everywhere, at any desired x. Therefore, I'm defining some E left. Let's call it with E underline left. E left is what? What is M? For the left boundary, we know that the electric field here is E1, here is E2, right? It should be like E2 minus E1, right? This is M divided by what? Divided by delta x. What is delta x? If this is H1 and this is H2, and because we are in uniform grid, both will be H. This one is H, this one is H, and this grid is at the center of cell. Therefore, this interval also should be H. Therefore, here delta x is just H, right? Divided by H multiple to the x minus x naught. We need to calculate the value of the electric field here. Therefore, x is 0 and x naught, let's choose this point as the x naught and y naught. Okay, therefore, x minus this will be h over 2. This is indeed half of h multiple to the h over 2, right? Plus what is y naught? We say that we choose E1 to be y naught. Okay, in the same form we will have E right. Just let me copy it from here, Control C, Control V, and one more thing, x minus x naught when x is 0 and x naught is the position of first non-integer grid, it will be negative. Therefore a minus should be here. And for the E right, we will have we will use this point, and this point, right? Therefore, it will be E and minus E and minus 1, again divided by h, multiple to the h over 2, because again this distance is h over 2, right? And what is E, what is y naught for the right boundary, and that one is E end. Now again, by sweeping of I from let's say 1 until n, and I want to assign E to the E total, EI to the E total I, or what? Okay, when we substitute, it should start from 2, right? It should start from 2 and we give I to, no, sorry, it should start from 1 and we give E1 to the E2 plus 1, right? And what will be the first element of E total? Indeed should be E left, E underline left, E underline left, 1. And the last element of E total should be E underline right. E total end. Okay, let's again copy it from here. Control C, Control V, and one more thing, because now the size of E total is different than the size of E, therefore let's define some xplot. Xplot can be like having of the left boundary. At the center we have x edge, and at the end again we have the right boundary, and this time we are plotting x plot total electric field versus x plot. Just let's check it. There's some error, and it said index exceed the number of the array 99. 99, line 19, at here 108, here the last n should be here should be n minus 1. Let's check it again. And you see what we did, we just calculated the electric field at the left boundary, and at the right boundary by the linear extrapolation of first two grid and last two grid. And here we have the total electric field, yes. And where is the electric field at the center? I think I need to put a figure here, figure. Okay, to have both. Yeah, this is the total electric field, and this one is the electric field only at the central grid, right? Okay. Okay, let's go to the first of the code and start modification. We will have the first layer. Let's define epsilon 1 to be 12, and I need to define new epsilon for the second layer. Control V. Let's define epsilon 2 to be some like 3. What else? This time definition for A is like this. We do not have the epsilon at the denominator, right? Therefore this time A is minus q divided by epsilon naught. Let's define the thickness of layer 1 with 1 and let it be, for example, 1 micron. And let's define the Control C, the thickness for the layer 2 with D2 and let it be 3 micron. And in general, the total thickness, that is D1 plus D2, will be the same for micron. Okay, and let's just save these thicknesses in some array like this. We have 0, we have D1, and we have D1 plus D2. Now we have the position of the beginning and the end of each layer in this DA. What else? Let's go. We do not change V left, we do not change V right, V thermal is the same. Here let's define N1. N1 to be the number of grid at the first layer, and let's define it with 51. And let's find X1 at the first position at the first layer. It should start from DA1 until DA2, and the number of grid should be N1, right? What else? Let's copy it again to define the number of grids for the layer 2. Let it be 151 N2, right? Here it should be N2, and X2 started from DA2 until DA3, right? And what else? The edge is different now. We need to have an array for the edge, and let's therefore the edge will be second, for example, grid number 2 minus grid number 1 will be H1. Grid number 3 minus grid number 2 will be the H2. Therefore it will be like half, not half this time. We need just have the delta x from 2 until n minus x from 1 until n minus 1. What these commands do, just it subtract the x2 from x1, x3 from x2, so on and so forth until the end. Let's take a look to the x2, to the appearance of the grids, just by plotting them, figure. Okay, I want to plot. I need to also define the x, therefore x will be what? X will be x1, x1 and x2. Okay, and I wanna plot x at some position. Let it be at 0 with some, let's say, with some blue dot, right? Grid on. What else? Nothing. Also, I want to see the format of delta x. Just again, Control C, Control V, delta x or h. I want to see plot h plus h with some, let it be red color, and let me disable all the rest. Control R and just see the format of grids and the format of h by pressing F5. You see we have some 0 at the delta x. Why? Because here we have a common x. The x end, x1 end and x2 1 both are the same, therefore h here is 0. What we should do, avoid such a 0 delta x, we need to just remove the last element of the first element. The first element of the x2 just by an empty bracket command. And once I have removed this one, you see this is indeed the h, and if I type h here, you see that the value of h for layer 1 and layer 2 at everywhere it is 0.2 times e minus 5. And because why? Because we have defined the same number of not same number of grid. The number of grid is proportional to the thickness of the layer. For example, if I put 21 here, you see that this is h for the first layer, this is h for the second layer, and this is the appearance of our grid. You see that we have more dense grid at the layer 1 and less dense grid at the layer 2. Also, I want to see the format of non-integer grid. And what will be the non-integer grid? Again, we have it here. We have defined non-integer grid somewhere here. Where is it? It was xh. Here. Just let me copy it. Control C. And have it after x. Control V. Therefore, this xh will be non-integer grid, and I want to plot it on the same window for x. Hold on. But xh at some, let's say 0.1 level, and let's define some limit for y lim be between -1 and 1. Okay, let's look at it again. xh at 0.1, why we do not see here xh at 0.1. Just let me mark it with some red dot. Here, now we see it. Indeed, if you zoom, you can see the format of the integer grid and the format of a non-integer grid. Just for visualization of our grid, you can do that, and just for checking that every delta x is non-zero, it's better to have a plot for the grids and for the delta x, and you can be sure about the value of delta x and the appearance of the grid. Now that we have different epsilon for different layers, we need to define epsilon. Let's do it here. let's define allocate some memory to the epsilon. It should be zeros n1, and we know that from epsilon should change epsilon from the first grid until n1. Epsilon should be epsilon 1, and from Control C, Control V, from n1 until n1 plus 1. From n1 plus 1 until n, epsilon should be epsilon 2, right? But we forgot to define the n, and what is n? N can be defined like n should be length of x, right? Press F5. Yeah, everything is okay, there is no error. And let me increase the number of grids also here to have the same delta x for both layer, and we have the same appearance of the grid. Okay, let's enable again these comments and edit them line by line. We do not change n1, we do not change n2. This is the indeed initial guess. Here this d should be indeed the total thickness, and total thickness is saved at underline A3, right? And we do not change this, we do not change this, do not change this tolerance, let it be like 1e minus 14. M should be here, we do not change it. Right hand side B, and we should notice that here right hand side B is epsilon 2v1 for the first element. Therefore we need to multiply this v1 with epsilon 2, epsilon 2 we left, and also for the last element of right hand side B matrix we have epsilon 8. Where is it? Here, epsilon 8 v1. Therefore this one should be epsilon n minus 1 or n minus 1. Both is the same. What else? We need also to, let's remove the force array from this right hand side B matrix just by writing right hand side B n1. We know that the interfacial grid is saved at n1, or it is located at the n1 position, and we remove the fourth line or fourth row by this empty bracket. We won't use this NC and we all see this time. Let's just remove them. What else? We know that this part is developed for grid by grid calculation. I'm just deleting this. And again, we don't use this. We all see NC. And okay, now let's modify this M definition that we have derived here. Where is it? Here, yes. We know that mi minus 1 I is epsilon I. Therefore, this one should be epsilon I. And this one should be epsilon I plus 1. I plus 1, correct? Check. Yes, and here at the center this time, because H is in the array format, therefore here we should add I plus 1 to this H, and also we need some epsilon here. Control C, multiple to the Control V, epsilon I plus 1, right? This one, I'm just modifying this term. Okay. Okay, everything is correct, and we have the same one here for the M11. What else? Okay. now we say that for I, when I is n1 minus 1, when I is n1 minus 1, we have some other definition for the element of this matrix. Control V, we know that mi minus 1, I minus 1 should be what? It should be here ah squared, and the same about the same command that we have here. This one just copied from here. Control C, Control V, but this time h is I, n is I. We have another term, fraction 1 multiple to the epsilon, right? Epsilon I, yes. Epsilon I minus 2 epsilon, again I, not I plus 1. Epsilon I, yeah. We forgot to define fraction 1 and fraction 2. Let's do it here. Fraction 1 is what? It is epsilon 1 multiple to the h5. h5 should be n1, right? Let's set it I, and again give and here let's give I to be n1 minus 1 for this command, and for Control C, Control V, and for fraction I should be n1, that is indeed 5. The number of grid is 9. Okay, this is epsilon 1 h5 divided by epsilon 1 multiple to the h I again plus epsilon 2 multiple to the h I minus 1. Right, this is fraction 1. And what is fraction 2? Control C, Control V. We know that fraction 2 is epsilon 2 h4. h4 should be hi minus 1 divided by the same term that we had here. Yeah, fraction 1 is epsilon 1 h5 divided by epsilon 5 h5 plus epsilon 2 h4. I think it's true. Let's continue, and we were here. Let's copy it again. Control C, Control V, Control V, Control V. This will be I plus 1, and term should be similar to this one, but I here we have I plus 2 instead of I, and fraction 2. Fraction 2, and all I should change this to the I plus 2. I plus 2, I plus 2, I plus 2, I plus 2. Okay, and I minus 1, I plus 1 is fraction 2 epsilon I. Which one? I minus 1, I plus 1. I minus 1, I plus 1 is fraction 2 to the epsilon I, and I plus 1, I minus 1 here should be fraction 1 epsilon I plus 2. If I do not make mistake, I plus 2, right? Yes, fraction 1 epsilon I plus 2, that's okay. Again, we need to reduce the size of the matrix. Here we need to remove the fourth row and the fourth column. Therefore, let's again define I to be n1 minus 1, and we will remove the fourth column by this command, and we'll remove the fourth row this command. Okay, what else? We defined new element of matrix, we reduce the size of the matrix, and this time I want to create the right hand side inside the loop for I should change from 2 until n minus 1. Why? Because the number of grid is 9 and the size of this matrix is 1, 2, 3, 4, 5, 6, 7. Therefore, it should start from 1 until n minus 2. N. Okay, and what is right hand side? Let's copy it. Control C, Control V, but here right hand side I, first one should be here I, we old I, thermal, not NC, it should be NI, again H I, and again not NC, H I. And let's allocate some memory for right hand side. Control C, here Control V, it should be zeros and minus 2 1, and after creation of this matrix, okay, just here we see that the first element is 2, not 1. Therefore, this, when I is 1, this one should be I plus 1, and also this one should be I plus 1, and I plus 1, I plus 1, I plus 1. Again, after creation of the right hand side matrix, we again should reduce the size of the matrix when I is 4. Right hand side I should be an empty bracket, and it will remove the row. Okay, what else? Therefore, we should hit this one, and the capital right hand side is defined to be right hand side minus right hand side capital B, and this time let's copy it. Control C, Control V, and let Control R here, and we have defined this matrix with values underline C underline VI, V underline C underline WI, V underline C underline WI will be inverse of matrix A multiple to the right hand side matrix. Once we created this matrix, we need again to create the total the whole matrix. What we need also add the V5 to this matrix. How? But we need to add V5 to the VC matrix here. You see, we have calculated this matrix. This one indeed is V underline C underline WI. This one is V underline C, and you see that. Let's define again a 4. For I from 1 until n1 minus 2, and we see that we give we give V underline C underline WI I to the VCI. From what? From 1 until 3, we see that the terms are the same. V2 is here, and V2 is here, V3 is here, V3 is here, 4 here, 4 here, and 3 is N1 minus 2. But we need to calculate V5 from the boundary condition that internal boundary condition that we defined. Therefore, we will skip the N1 minus 1, and we start again from N1. Therefore, this one N1. From I from 1 until N1 minus 2, we give V underline C underline WI to the VCI, and we need to define VCI here. Underline C should be zeros and minus 2, 1. Okay, we will skip N1 again, another for loop, Control C, Control V, and from N1 until N minus 1 we give what? For example, imagine that I is 5. When I is 5, we need to give V underline C underline WI4 to the VC5. Therefore, here should be a minus 1. When I is 5, it will be V underline C underline WI4. What is that element? That element is V6. And where is V6 at the VC? V6 is at this position, at the VCI, right? Okay, that's why I just created this slide, and just by looking to the slide you will understand which element should be assigned to which element from one matrix to the other matrix. And we have skipped N1 minus 1 for fourth grid. Therefore, when I is N1 minus 1, we know that we underline C I should be calculated from its neighboring point according to the this one, fraction 2 V6 plus fraction 1 V4. Fraction 2 multiple to the VCI plus 1. Why I plus 1? When I is 4, VC5 should be V6. You see that VC5 is here and this is V6, and VC3 is V4. Therefore, it's just calculated from its neighbor, this element. Fraction 2 plus V underline CI plus 1 plus fraction 1 multiple to the V underline C I minus 1. Okay, what else? And after calculation of VC, we give this VC to the main V, and after having the V, we calculate the error, and we have discussed about this part in the previous video, so we do not have any change here. And what we need also change, we need to change this I that we defined here, because this time H is array. This should be HI. This one, because at the first layer all H is same. We have the same delta X for entire of the layer 1, the same delta X for entire of the layer 2. Therefore, here in calculation of the potential at the left boundary, let's put H1 here instead of H, and here let it be H end, because for the layer 2 all H is the same. I put H end here to avoid any error. And one more thing here, we have defined the size of matrix M here. We need to cut it from here and put it here, because at each loop you see that we reduce the size of the matrix. If we do not have this command, therefore size of M matrix at each loop will reduce, and it gives us some error of a mismatch between the dimension of the matrix. I think now everything is okay. Let's press F5 and see, is there any possible error or not? Yes, there is some error, and it says that in line 180 VCI minus 1. Here, what is the size of? No, we have not defined the size of VC. Here, this one should be n-2, not n-1, because we know that the maximum size for a central grid is 7 when number of grid is 9. Therefore, the maximum size for the VC is 7. It's F5. And we have such a form for the potential. This is for electric field. I think something is not true. Let me check. Just let's close every figure. Close out. CLC. Let's press F5 and see where is the mistake. Such a sharp changing in electric field is not very logical, and why we do not have this convergence. Figure for errors here. I disabled. Control T. Let's see, do we have convergence? Yes, we have convergence, but the appearance of the potential and the electric field is strange. Main part here. Everything okay here, child, and here. Close out and just check formula here. I think here it should be fraction 1. Okay, and press F5 again. Yes, I think now it's okay. And we have 2 electric field. Let me disable the electric field for the central grid. Which figure? This one. See the total electric field. Okay, one more time. This is the electric field that contains the field for the boundary, and this is the convergence, and this is the potential. But let's reduce the N1 to avoid such a sharp changing in the electric field at the boundary. Let's reduce it to 1E12. It's F5. And now we see something. This is the convergence, and the error, the tolerance is defined here. Let it be 1E minus 12. Where is the tolerance? Because 1E minus 12 is also enough for us. Press F5 again. And this is electric field, and this is the convergence, and this is the potential. Just let me also reduce this. We left from minus 0.1 to minus 0.2. And we clearly see that there is a crack in the potential, and due to such a crack in the potential, due to the changing of the epsilon from the layer 1 to the layer 2, we see such a discontinuity in the electric field. What does it mean? It means that if I just zoom it here, if we want to calculate the derivative of function at this point, at the position corresponds to the 1 micrometer, that is interlayer between layer 1 and layer 2, if we approach to this point from this from the right side and try to calculate the electric field, we will get this value for the electric field, and if we approach from the left, we will get this value for electric field. And let's check if we have single layer just by changing of potential from changing of the epsilon from 3 to 12, we should not see such a crack. Let's check. And you see that there is not any crack in the electric field close to this boundary of the two layer. What else? I think that's it. Just as a final remark, again, let me change this from 12 to 3, and you see that we have some crack. And just let's have a look to the grids, and you see that we have the same grid, I mean the same grid density for layer 1 and layer 2. But what if I just change the number of grid in one of the layers? Let's, for example, reduce it from 100 to 51 and let it be just 101, and let's put it 12 again for the epsilon 2. We should not see the crack, but we see some crack. If you notice here, and that if we have some zoom here, it is not very clear here, but at the electric field you can see that there is some discontinuity in the electric field. Here, you know why? Because we derived the discrete form of this PDE for a uniform grid. Now that we have a one layer, because epsilon 1 and epsilon 2 is the same, but grid is not uniform here. You see that until some point we have dense grid. You can easily see here we have some dense grid at the left layer, and we have some less dense grid at the right layer. That's why you should be careful if you want to have some arbitrary grid. If you want to have some non-uniform grid, you should use the definition of the derivative using finite difference for a general non-uniform grid. But this, in the theory, we have derived the discrete form of the equation for uniform grid. Therefore, you should be careful that the density of the grid or the grid should be uniform in whole of the layer. Therefore, when the thickness of this layer is 1 micron and thickness of the second layer is 3 micron, therefore for the layer 1, when this is 51 and when this one is 151, right? Now we will have uniform grid and we won't see any crack in the potential, and we should not see any discontinuity in the electric field. But again, we see something. Why? You know why? Because now in this code, what we do, we assume that we have some internal boundary condition, and we calculate the potential at the interfacial grid using this equation. Which one? We are using this equation, but we are not allowed to use this equation when we do not have any interfacial grid. We should use this equation. Therefore, we need to modify this code slightly. How? Let's go start from here. The point that we have reduced the size of matrix. For example, for right hand side P, let's say that if epsilon 1 is equal to epsilon 2, do nothing else, and cut it from here, Control X, else just reduce the size of this matrix for the grid number corresponds to the interfacial grid, right? We should have the same, Control C, for here. We should not have this new definition for the matrix M when there is not any interfacial grid, right? Therefore, I just define the same condition. If epsilon 1 is equal to epsilon 2, do nothing. Otherwise, we should add these new elements to the matrix M and reduce the size of the matrix. 1, 2, 3, 4, just 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's just for beauty of the code. 1, 2, 3, 4. 1, 2, 3, 4. Again. Okay. And again, we need same command. Control C. We need the same command where? Here, yes. Control V. 1, 2, 3, 4. 1, 2, 3, 4. And similarly, we should put commands inside Control X. This if else. 1, 2, 3, 4. And also we need to put these commands. Control C here. Control V. And here, if epsilon 1 is epsilon 2, we should use this command for calculation of VC. Control X, Control T, Control V. Otherwise, we should calculate the VC using first calculation VCWI, then calculation of VC. Therefore, Control X, Control V. 4, 1, 2, 3, 4, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 3, 4, 3, 4, 3, 4. Okay. For when epsilon 1 is equal to the epsilon 2, this crack or this discontinuity should not appear. And by pressing F5, you easily can see that there is not any discontinuity in the electric field. Okay. There is not any crack in the potential, but when epsilon 1 is different than epsilon 2, we have this discontinuity in the electric field and we have such a crack in the potential. I think that's it for today. If you have enjoyed this video, do not forget to like it and share it with your friends. And just I sweep this code toward down, and if you want to regenerate the same code, you can easily pause the video and start to write what you see here. Almost to the end. Yes, that's it. Thanks for your attention. See you later.